Welcome to the second video in Work and Energy. In this video, we'll look at how to calculate the work done by a constant force. So for us, luckily, we have a fairly common situation where there is a constant force acting on an object, which is our force due to gravity. So as an example, we have an example that you've already seen. We have our supply plane dropping off a parcel to a remote village. So the plane will release its package when the package is in a line of sight displacement or displacement S from the village, as shown in the diagram, and we know that the initial vertical velocity of the particle is 0. So neglecting air resistance, how would you go about finding the work done by gravity on the parcel? Which equations would you use? So if you wish, you can pause the video here and work through the problem yourself. Otherwise, we are looking for the work done by the parcel, the work done by gravity on the parcel. So that tells us we're looking for the components in the y direction in this case. So I'm going to redraw my diagram to show the components the things that I know in the y direction. So I know that we have the force due to gravity acting downwards, and I know that we have our displacement in the y direction. We also know that we have the formula for work. So the work is force times displacement, or it's also equal to the change in kinetic energy. And this gives us two ways that we can solve this problem. So the first way, we can use the first equation, so force times displacement. In this case, we know that we want the work done by gravity. So as I said, we're looking for all of the work done in the vertical direction. So we need then our force in the vertical direction, in the y direction, which is mg, and we also need our displacement in the y direction, which from our diagram we can see is equal to s cos theta from our standard right-angled triangle and our trig. And that means then our work done by gravity is equal to fg times sy, which is mg times s cos theta. So as a quick check, we're told that we're looking for the work done by gravity on the parcel, which means that we're looking for positive work. So we know that, or in general, our force due to gravity, as I said, I always make that negative because it's going downwards. And we also have our displacement y, which is also in the negative direction. In this case, it's also downwards. So we have a negative times a negative, which means that our work done by gravity on the parcel will be positive. So that's a nice check. Our second option for solving this problem is to use our equations, the second equation, which is that work is equal to the change in kinetic energy. So work is equal to half mv squared minus u squared. So again, to find this, we want the work done by gravity, which means we need our components in the vertical direction. So from this formula, we need our initial velocity squared, and we know our parcel was released from rest, so that's 0 meters per second. And we need our final velocity squared. And to calculate our final velocity squared, we use our equations of motion. And we can see that we need both our acceleration in the y direction, which we know is equal to gravity, and our displacement in the y direction, which we have also previously calculated. So once we substitute these values into that second equation, we find that our work is again equal to mg times s cos theta. So both of these ways work. I prefer the first way because it's simpler, whereas the second way requires an extra step. But whichever you're most comfortable with. And there are some more examples for calculating the work done by a constant force following this video.